Now, in the previous cases, we talked about the situation where the particle have a constant surface charge density or constant zeta potential. Now, this kind of situation can only appear if the particle is either non-conducting, perfectly non-conducting, perfectly dielectric, or perfectly conducting. So, in that case, we can consider a constant surface potential, but that surface potential is depends also on the external electric field. Now, if the particle is even in the O'Brien-White analysis and all, the permittivity of the electric permittivity of the particle was neglected and found it has got no effect on its electrophoresis. Electric polarization of the dielectric particle due to imposed electric field induces a non-uniform surface potential. Now, what happens if it is a dielectric particle, unlike a conducting particle? So, it does not have any free charges. So, in that case, there will be a electric field penetration of the inside the particle, and there will be a formation of surface charge density, which becomes a non-uniform, and it is a function of the external electric field. So, O'Brien-White demonstrated through the weak field analysis that the electrophoretic mobility does not depend on the particle dielectric constant. However, in recent years, there are several theoretical analyses and experimental results suggest that the role of electric polarization of a dielectric particle on electrokinetics. Now, this charge density that appears due to the electric polarization of the particle is we call as the induced surface charge density. So, that is non-uniform, that is one problem. Another is depends on the applied electric field. So, in that case, so that means the electrophoretic velocity in that case becomes a nonlinear function of the applied electric field. So, you cannot impose the mobility only on the that means it electrophoretic velocity depends nonlinearly on the electric field. So, we cannot have a electrophoretic mobility, that is linear variation no longer exist. Now, how to model this kind of a situation? I will just give the overview to model a electrophoresis of a dielectric particle. So, now the dielectric particle is characterized by the dielectric permittivity ratio given by this epsilon r. This is the permittivity of the particle, electric permittivity of the particle, and this is the liquid. So, this ratio. Now, if this ratio is very low, so that means the permittivity of epsilon p is negligible. So, we can consider it is a non-conducting, and the previous analysis is holds good. But if it is very large, then also it is a perfectly conducting. So, these are the two extreme situation. Now, we are considering that where epsilon r is not negligible. So, that means we have a polarizable particle. Now, if the particle does not contain any free charges within the within itself, so what we will have is the inside the particle. So, what we will have this del 2 phi 2 equal to 0. So, what we are doing is this is the electric field we are talking about, this is the electric potential inside the particle, and this is epsilon r, and the dielectric permittivity epsilon p, and this is epsilon e. So, this is the equation if there is no free charge within the, there is no net charge within the particle. So, delta phi 2 equal to 0, but on the surface of the particle, that is the electric displacement condition that we have derived in the very beginning, will be governed by this way. This is for the continuity of the potential phi 2 equal to phi 1, and there is the electric displacement condition. So, phi 1 is the one which satisfy the Poisson equations and all these equations. So, here we are outside the electrolyte medium, this the potential is governed by the superscript subscript 1. So, it follows the same equation, only thing is that it satisfies this condition at the surface governed by this way, and epsilon r is the permittivity constant. So, this is the only delta phi 2 equal to 0. So, this is the only modifications which has to be taken into account, that on the surface we cannot have a particle to have a constant potential or constant charge density. This is one aspect. Another aspect is that the particle velocity and surface charge density becomes a function of the electric field. Now, in this case there is we consider the full computational model. I just highlight how it differs from the situations where particle is taken to be a non-conducting one. So, if we consider the particle to be a polarizable particle, so this surface potential is can be obtained and governed by this following this curve is axis symmetry. So, we have taken 0 to pi. So, what we find that as epsilon r, epsilon is the permittivity ratio. So, that means as epsilon r is increasing, the surface potential is following a nice sine curve, and it is approaching a becoming independent of epsilon r after beyond a certain value of epsilon r. That means the particle is behaving like a conducting particle. And also you see these from this figure, the surface charge surface potential, here it is the surface potential, it depends on this applied electric field. Here beta is the scaled electric field, E0 is the applied electric field, and we define beta as the scaled one given by this way. So, if I consider a high electric field, though the large variation in the surface potential is evident. If it is low, then it is smaller compared to this. So, obviously, the surface potential strongly depends on E0. So, this implies that the electrophoretic mobility will also be a function of E0. So, that is why mobility is not used, the term mobility is not used, the velocity is used. Now, electrophoretic velocity is found to reduce. Now, there are several there are physical mechanisms for a reduction, because as the surface become polarizable, so the surface conduction effect becomes significant. So, the surface conduction effect reduces the mobility, electrophoretic velocity. So, that is why what you find that electrophoretic velocity reduces as the ratio epsilon r is increased, and the velocity attains a saturation at large value of the permittivity ratio, for which the particle behaves like a perfectly conducting particle. And also what I see is that the surface charge density depends on the applied electric field, hence the electrophoretic velocity varies nonlinearly with the imposed electric field. Now, this result, this is the showing the ratio of electrophoretic velocity between a polarizable particle and non-polarizable particle. Non-polarizable means epsilon r is very, very small. So, what you find that this ratio is deviates by a large extent, and it is always less than 1. So, that means See, this UE by UH is always less than 1. So, this implies that the electrophoretic velocity is low when we consider a polarizable particle. Here we have taken epsilon r and large at 50 and dy length is large, k is large, so dy length is low, small. So, smaller dy length and larger epsilon r for different choice of the surface charge density sigma. In the beginning, the particle have a surface charge density sigma, and due to polarization there will be additional surface charge formation, electric polarization, and the what we find the a great deviation is occurring, and the deviation is prominent where sigma is large and electric field is large. This is the scaled electric field. So, as the electric field is becoming higher, so what we find that the deviation is becoming significant between the non-polarizable and polarizable and non-polarizable particle. So, which this results precisely shows that the dielectric particle solid polarization is not a negligible effect when you have the permittivity ratio is order 1 and the electric field is strong. So, this kind of situations. And another thing is that this nonlinear electrophoresis cannot be solved by this Henry model or even the first order perturbation as done by the O'Brien, White, Weismann and other things. So, in that case the nonlinear situations one has to rely on the computations of the governing equations. Now, next, and this will be our last topic on electrophoresis is gel electrophoresis. Now, this gel electrophoresis is a very important aspect in electrophoresis, because through the gel electrophoresis the shorting of particles and DNA and other things can be done very nicely or efficiently, and also gel has advantages that the gel can be used several times. Another thing is that the Joule heating effect is low in the hydrogel. Now, Joule heating effect we have not discussed. Because of the Joule heating effect, these ion migrations and all, there will be a generation of heat loss, and that way the energy loss will arise. So, the aim will be to reduce amount of Joule heating. So, which is good in gel electrophoresis, and also the dispersion is low. So, that is why gel electrophoresis is a very important technique for manipulation of DNA, RNAs and all these things in biocolloids and all. So, we will give a little overview of the gel electrophoresis. Now, what is the gel electrophoresis? Is that the particle, the colloid particles are suspended in a hydrogel medium. So, this hydrogel medium, which can be modeled as a homogeneous porous medium, that is saturated with an aqueous electrolyte. So, the gel electrophoresis becomes different, because now here we have the medium as a homogeneous porous medium instead of a electrolyte medium that we have discussed in the previous cases. So, now this creates some new phenomena compared to the previous one. One is the long range hydrodynamic effect, that is called the Brinkman resistance, and there is a short range steric effect. Steric effects when there is a friction with the gel pore and the particle. Now, this long range hydrodynamic interactions in hydrogel are governed by the effective medium approach, in which hydrogel is modeled as a continuum and the hydrodynamics are governed by the Brinkman equation. So, the effective medium approach, what we do is hydrogel is modeled as a homogeneous porous medium and is characterized by a screening length parameter, hydrodynamic screening length. This screening length is also related with the permeability of the porous medium, and also the short range interaction. This is important when the gel pore size are comparable with the particle size. Now, if I assume the gel is highly permeable, so in that case these short range steric effects can be taken to be negligible. So, and also there are several models through which the steric effect can be estimated. So, in this one can assume that steric effect has not a significant importance when we have a hydrodynamic screening length of the gel is quite large compared to the particle size. So, if we consider a dilute gel, that means the screening length or permeability is high. So, in that case these steric interactions can be neglected. Now, we consider the electrophoresis under an externally applied electric field E0 of a non-conductive spherical particle of radius a with uniform surface charge density sigma submerged in an electrolyte saturated gel medium, and we model the gel medium as a effective Brinkman porous medium with screening length as L, which we assume to be lower than the diameter of the particle, and the screening length is also measures to which extent the fluid can penetrate within the hydrogel. Now, under the applied electric field, the particle acquires the electrophoretic velocity UE relative to the surrounding medium, and this UE is to be obtained, which is unknown a priori. Now, the governing equations in this case to take into account the flow through porous medium is accounted by the Darcy-Brinkman equation, and the ion transport, which is governed by the Nernst-Planck equation in the electrolyte, and the Poisson equation, which determines the electric field in the hydrogel medium. So, these things are there. Only thing is that the gel hydrodynamic resistance has to be taken into account through some terms. Now, before we write the equation, what is Darcy law? Now, Darcy law, when there is a flow through a porous media under a pressure difference, say along a length scale pressure difference in a cross section area A. So, the Darcy law through experiment Darcy measures that the fluid discharge amount is related by this way, where K is the proportionality constant, which is the permeability, which is referred as the permeability, and this is the pressure drop along the length L. A is the cross sectional area, mu is the viscosity of the medium. So, now if I write it Q by A and also the velocity, if I write in terms of velocity, and this is the pressure gradient, and there is a negative sign because the pressure increases, velocity decrease, negative sign, fluid flows from high pressure to low pressure, so opposite direction. And if I consider only unidirectional flow, so this can be simplified form is governed by this equation, this form. So, in a porous medium, the fluid flow can be determined by this equation, but this is not a complete equation, particularly when you have the boundary effect is there and also the permeability is not permeability is high. So, that means gel screening length is high. So, in that case we cannot have a Darcy law is not sufficient. For that, this Brinkman extended, Brinkman take into account extended or modified the Darcy equation by taking into account the viscous stress, and that gives the several simplification. One is the this is a kind of analogues to the Navier-Stokes equation, and if you have a interface porous and fluid, so this Brinkman equation is works very nicely, because the momentum equation have the viscous shear stress in both the Navier-Stokes equation as well as in the Brinkman terms. And also if you have the permeability is high, shows viscous shear stress becomes an important thing. So, the governing equation in gel medium, or the governing equation for fluid transport in a gel medium is governed by this equation. So, this is as usual, this is the Navier-Stokes equation. So, you have an extra term here, this is the Darcy term beta square u, this is the because of the electric body force, and this is the shear stress, viscous shear stress. Mu is absent here because of the scaling. We have taken the velocity scale as this is the non-dimensional equation. So, mu is absorbed over here, rho is also absorbed in P. So, this is a scaled equation, and this is the equation for continuity as usual, incompressible flow. So, we have a electrolyte saturated porous media. So, the electrolyte are flowing, or the flow of the electrolyte is governed by this equation along with the continuity equation, and this parameter, this measures the scale parameter for the porosity permeability in defined by this way. So, L is the hydrodynamic screening length of the gel, L is also can be written as root Kp, Kp is the permeability. So, higher value of beta implies a lower permeability of the gel medium, and because this is inverse. Now, the ion distribution within the electrolyte is governed by that Nernst-Planck equation. So, if I write the Z electrolyte, because here it taken plus and minus. So, or 1 electrolyte, Z is the valence is taken to be mod Z as 1. So, we get the Nernst-Planck equation governed by this transport equation. Again, this is the convective transport of the ions, diffusion, electromigration. So, this valence, and this is the Poisson equation for electric field. Rho is the charge density given by this way. So, this set of equations are governing the electrophoresis in a hydrogel medium. So, if we look back to the previous one, so only difference what we find is the addition of this term beta square u, which was and the gel contribution of gel is coming through this beta, and beta is determined through the permeability of the medium. So, one need to study this set of equations. Here of course, we have taken the gel as uncharged. So, that means the gel skeleton is uncharged. So, that is why charge density of whatever appears in rho e is because of the movement of the electrolyte within through the hydrogel medium. Now, the boundary conditions we can impose on the surface of the sphere are equal to 1, we have u equal to 0, and this condition that surface charge density, if you have a constant surface charge density is governed by this way, and the no normal flux of the ions on the surface. So, this is governed by this equation. This corresponds to no normal flux, no ion penetration through the surface of the sphere. Far away from the surface of the sphere, that means when r is many times greater than 1, u is approaching to minus u e. Again, we are taking the particle to be stationary and fluid is approaching towards the particle, and phi is becoming the imposed electric field, and these are the bulk value, because this is far away from the sphere. The electrolyte is neutral. So, you have the same ionic concentration. So, is scaled, of course. So, it is N0 is the bulk ionic number. So, it will be the N0, and we need to find out the forces, and through the force balance we can obtain the mobility, mobility or electrophoretic velocity. Both are the same in this case, because here we are considering the linear situation, linear with respect to the electric field. So, we need to find out the electric force and the hydrodynamic drag experienced by the particle. Electric force, again one can compute through the Maxwell stress, and hydrodynamic drag from the shear stress and pressure drop and all these things. So, now I show some result. So, this is the streamline pattern for gel electrophoresis. So, what we find here, the deformation of the double layer. So, this is the counter ion distribution. So, here you see this streamline. So, that means electric field is applied and the fluid is moving along this direction. Here we kept the particle to be stationary, and so the particle is kept to be stationary. So, in that case the fluid is approaching from the other side, opposite side, the propulsion of the particle, and the deformation of the double layer is quite evident, because we have the particle to be moving this direction. So, the ions are dragged downstream direction. So, this direction will be downstream for the particle, because particle is moving on the direction of the electric field, positively charged. So, the mobility, there are several authors have obtained the mobility. So, based on the computations of those nonlinear governing equations, one can obtain the mobility. Some of the, so with the experimental results and theoretical analysis, we made a comparisons. Now, what we find is the electrophoretic mobility, which is scaled, of course, is varies with the Debye length. So, after certain value of Debye length, so it attains a saturation, a constant value. So, we get a, and this is the based on a perturbation analysis, the allusion. So, we find a large deviation, particularly when zeta is large, and also this is the mobility versus the permeability beta. So, the mobility is large when the permeability is high. So, that is beta is low means permeability is high, because beta was defined as A by L. So, L is large if beta is low. So, permeability is high means the electrophoretic mobility is high. So, as permeability becoming low, that means the gel becomes dense, it is decreasing and slowly becoming vanishing over there. So, that is how the gel electrophoresis can be modeled. So, in modeling the gel electrophoresis, what we need to do is we have to extend the Navier-Stokes equation to the Darcy-Brinkman equation, where the Darcy terms which takes into account the hydrodynamic resistance provided by the gel skeleton, and long range effect is good enough if we have the gel is quite dilute. If not, then we have to consider the steric effect. Now, there are several correlation formulation for steric effect, which is available in the literature. So, with that I conclude for the electrophoresis portion. Thank you.